All right, we're going to talk about local extreme or extreme values of functions today as our notes. And if you look at your screen, you'll see that I have a PowerPoint that I will share with you on the homework website. So let's get moving. The textbook gives the following example at the start of chapter 5. I like this example because it's a real life example. The mileage of a certain car can be approximated by this function, m of v, which is a cubic. And this function basically suggests that if you drive a certain speed, you will get a certain gas mileage. And the question is going to be for this, at what speed should we drive our car, or velocity should we drive to get the best gas mileage? So what we need to do is find a maximum of this function. All right, and you know, we can't necessarily model gas mileage. It would be different for every car, and we'd probably have a few bits of data, and then we could do a regression, and there might be a million different models for mileage per velocity, but we're just going to pretend that this one works. And you might say, okay, well, we could solve this graphically, Mrs. Muller. Why on earth do we need calculus to solve this? Because we could take our calculator and we could set the window, x min at 0, x max at 100, the scale at 10, and of course, we probably want to drive faster than 50 miles per hour, but that's another subject altogether. Anyway, we could adjust our window, and then we could actually have our TI-89 graph this for us. And you could say, well, Mrs. Muller, all I have to do is hit F5 math, and I can find the maximum of that function without any calculus at all. And you'd be right. But there used to be a time when we weren't able to find maximums with calculators, and we had to use some math ingenuity, so to speak, to solve for the maximums of functions and the minimums of functions. And so we use some calculus to do that. And so it's worthwhile to understand that process. And obviously, if you do that, you do this on your own calculator, you'll see that the maximum velocity that you should, or the maximum velocity occurs at 38.6 miles per hour, and you will get 32.12 miles to the gallon. And I don't know very many people that would like to drive 38 miles per hour. But anyway, it's just an illustration of the fact that, yes, I am acutely aware, and so is everybody else. You could find the maximum of a function using a graphing calculator. All right, but let's notice at the top of the curve, what kind of tangent line do we have? Well, we have a horizontal tangent line, and obviously their slopes are 0. And in calculus, we have a way of finding where horizontal tangent lines are. So we're going to go back in time and pretend as though we didn't necessarily have a calculator when we do all these problems, and see if we can find out where the extreme values of functions are. So let's go over some vocabulary first. And the first one is absolute extreme values are either maximum or minimum points on a curve. And we in honors pre-cal or pre-cal called these extrema, and maxes and mins. So that's nothing new. They're also known as global extrema. So if you ever see a question, find the global extremes, you'll know that that's the same as absolute. Extrema is the plural for extreme. So it's Latin, and all you Latin folks can verify that, but extrema means more than one extreme. All right, so moving along here. I'm going to give you some examples here. You can find extreme values of functions in the interior or the endpoints of a function. And now this function is very familiar. Y equals x squared, the domain's negative infinity to infinity, and open interval here. And clearly we have an absolute minimum at x equals 0, and the value is 0. But we don't have any absolute maximum, because the the end behavior rockets off to infinity in both directions. So what if I take the same function and I restrict its domain from 0 to 2? And this changes the problem a little bit. And now we have an absolute minimum and an absolute maximum on a closed interval. But of course, I obviously can't leave things alone. What happens if now this point right here is at x equals 0 an open dot, which means we have an open interval here at x equals 0? Well, then we could play this game here to see if we could find an absolute minimum, and we could say, all right, well, I could say that my lowest point is 0.1, and then someone else could say, well, I could get closer and say 0.01, and then we could go 0.001, 0.0001, and we could play this game, and nobody is going to win because we could get infinitely close to 0 and not ever get there. So in this case, we don't have an absolute or relative minimum in this case, and we only have an absolute max. So what happens if both ends are open? Well, if both ends are open, then we have no minimum or no maximum. And here we come to our esteemed extreme value theorem. This is one of the big 6 theorems in calculus. Extreme value theorem states if f of x is continuous over a closed interval, then a maximum and a minimum value will exist for that function. And essentially it's saying that you will be guaranteed an absolute max and an absolute min on your interval. I like to generally draw pictures. So, here's the first one. Now, if we look at this first picture, we can see that we have an absolute maximum and we have an absolute minimum, but where do they occur? They're occurring at the interior points of the interval. And then we have relative extrema on the endpoints. What about this curve? Well, this curve, we do have an absolute max and an absolute minimum, and no extrema on the interior of the function. So your extrema are occurring in this case on the endpoints. And then lastly, we have a combination. We have the absolute minimum occurring at one of the endpoints. The absolute maximum is occurring at one of the interior points. And we have a relative or local minimum at the endpoint. So in looking at this, we can see or tell that we have some possibilities if we were going to be looking or on the hunt for extreme values. We'd have to check out the endpoints and any possibilities that might be extrema on the interior of an interval. All right. So local extreme values or relative extrema, which is what we used to call it in pre-calculus. A local maximum is the maximum value within some open interval. Now, maximum value means maximum y value, and they occur at certain x's. A local minimum is the minimum value within some open interval, and that is a local or a relative minimum, and that means it's the lowest point, y value, at a certain x. All right, so this is obviously a unique function, and we're going to try to see if we can discover where extrema might occur. At the end here, we have an absolute minimum, clearly, because that's the lowest point on this function. And then what happens at the next extrema point, it's also a local minimum, in its little neighborhood there. And then we have a local maximum that happens next. And as we move right, we have a local or relative minimum. And then at the very top, we have an absolute maximum. And that absolute maximum is also known as a local maximum because in its neighborhood, it is the highest y value around. And then at the end point, we will have a local minimum or relative minimum. Now, interesting things are happening on the interior of this function when we have extrema. And what's really cool about this is, there's my relative extrema notation, is I want you to notice that at the local extremes in the interior of this function, if we have a 0 slope, it seems like we have a possibility of a max or a min. And if we have an undefined slope, let me go back, maybe. If you have an undefined slope, which is right here, that's also a possibility. of a absolute or local maximum. All right, so we're going to define that local extreme values can occur on an interior of a function, interior meaning not at the endpoints, if f prime of x equals 0. That's for sure. And then consequently, we're going to also just define a critical point as the area or the point of a function in which the derivative is 0 or it doesn't exist, which means it's undefined. Now, stationary points are when the derivative is equal to 0. And I liken that to physics, where the first derivative of a function, position function, is its velocity. And if the velocity is equal to 0, your particle or your body that is in motion is stationary. So they call critical points where the derivative is equal to 0 stationary points. All right, so critical points occur when the derivative is 0 or undefined. Now, an important note here. Sometimes if you have a 0 slope or you have an undefined situation for the first derivative, they may or may not be extrema. So this just gives you the pool of numbers where you will find them. So it might not always be an extrema, but it's a good place to start. All right, so we're going to use an example here. Let's say we do one of my favorite functions, which is f of x equals x to the 2/3. That's a power function, and it's my famous seagull one. And I have a closed interval here, -2 to 3. And so because of the extreme value theorem, I know I'm guaranteed to have an extrema that's absolute max and an absolute min. I just don't know whether those are occurring at the endpoints of that interval or in the interior of the interval. So what we're going to do is we are going to, first of all, now I know all of you are pretty bright and know what this function looks like and have a pretty good idea of where the extrema are going to be, but I'll show you a picture of it in just a second. So let's take the derivative. Well, when you take the derivative of x to the 2/3, all at once here, what do? We go power down function, lower the power 1, and we get 2/3 x to the -1/3. And then we're going to put things where they belong, meaning we're going to get rid of the negative exponents, and we'll say, okay, so this is equal to 2, the derivative is equal to 2 over 3 cube root of x. Now, it's really easy to see that there are no values that'll make this derivative equal to 0, but there is a value when x is 0 that'll make the derivative undefined or not exist. So that's my critical point, is going to be at x equals 0. And because x equals 0 exists in the original function, we can use it on my evaluation. So we're going to check the endpoints and we're going to check the critical point. So the first thing we'll do is check the y value of the critical point, which is at x equals 0. When we can see that when we plug in 0, we get 0. That's easy enough. All right. And now we have to see if that's a max or a min. We need to check some points on either side. So let's try f of -1. Well, f of -1 is equal to 1 when you plug this in, because you take the cube root of -1, you get -1, square it, you get 1. So it's positive on the left side, and let's try 1. When you plug in 1, you get 1 in the original function, and so it's positive on the right side. So since it's positive on either side of this function has a minimum at x equals 0. And it must be a local, at least. It might be the global, but we have to check the endpoints to figure out if it's an absolute or global minimum. All right, so let's check at x equals -2, because that's the left side of the domain restriction. So we plug in -2. Well, the cube root of -2 is just a cube root of -2. And then when you square it, you're going to get a, cube root of -2 quantity squared. And if you put it in your calculator, you get about 1.5874. 1.5874, right. And then let's see what happens at x equals 3, which is the other endpoint of our interval. And we would say f of 3 is equal to f 3 to the 2/3, which is about 2.08008. Now, At x equals 0, that still looks like it's the lowest point, so that's going to be the absolute or global minimum. At x equals -2, since it's decreasing afterwards, that's going to be a relative or local maximum. And the same thing's going to occur at x equals 3. So let's see what happens when we look at the graph. And so we can see that this is our classic x to the 2/3 that I like so much. And at x equals -2, this is a maximum here, but it's not as high as the maximum value at x equals 3. So we have to call at x equals 3 the absolute maximum, x equals 0 is the absolute minimum, and to the left here, x equals -2 is going to be the relative maximum. So how do we find these maxes and mins analytically or algebraically? Well, the first thing you do is you take the derivative of the function and set it equal to 0. And then you find out where the derivative is equal to 0 or it's undefined to find the critical points. Then you find the value of the function at each critical point and find values or slopes for points between the critical points to determine if the critical points are maxes or mins. And I will show you more examples about this as we go along. And then number 4, you check the closed interval endpoints to see if those are extrema as well, because the bottom line of this lesson is that you can have local or absolute extrema at the interiors of an interval or at the endpoint. So we must check both. All right, so critical points, as I mentioned a minute ago, are not always extreme values. And no, I'm not trying to trick you. It's just what's really cool about critical points is that at least it gives you several numbers to check. So I'll give you a classic example of a function where you have an extrema possibility that doesn't turn out to be a max or a min. So our toolkit function, y equals x cubed, if I graph it here, if you take the derivative of this, which we're all able and capable of doing, we get 3x squared. And hold on, let's go back. I need to fix my presentation here so that I can put the derivative here. If you take the derivative of this, you get y equals 3x squared. Well, when is that equal to 0? Well, that's equal to 0 when x is 0. And you can see that you have a horizontal tangent here at x equals 0, but it's not an extrema. Something else is going on with this function, and it has to do with concavity. It could be a possible point of inflection where it's concave down and then it becomes concave up. So sometimes critical points are not extrema. So moving along here, I've got another classic toolkit function, which is the cube root of x. This one, if you take the derivative of it, you will see that if you take the derivative, it would be 1/3 x to the -2/3. And if you put things where they belong, you would notice that this is a vertical tangent here, and the derivative is undefined. Well, that's a critical point, which turns out to not be an extreme value of a function. So that's another possibility. All right, so these are my Cliff Note versions of 5-1. All right, absolute extreme values. Functions can have more than one absolute or global max or min, meaning that you can have them occur at more than one value of x. And there's still, this would be an absolute minimum, this would be an absolute minimum, and they occur at the same different locations, but they're the same y value. So keep your eyes open for that. Absolute maxes or mins are also considered local or relative maxes or mins because in their little neighborhoods, they are the lowest y value. So they're all absolutes are always local or relative. Just a quick review of the extreme value theorem. The extreme value theorem states if f is continuous on a closed interval, a, b, then f has both a maximum and a minimum value on the interval. And this is my picture, you know, my famous f of x function. I have an absolute maximum of this f of x over the closed interval a to b at x equals b because it's the highest point and it's on an endpoint. I have an absolute minimum that occurs at x equals m, which is on the interior of the function, and that's where we have a 0 slope here, so pay close attention to that. And then we have a local minimum at x equals a, and we have a local or relative maximum, and I should have a max on my notes here, at x equals 0. And the bottom line with the extreme value theorem is that when you're checking for extrema on a closed interval, you must, and I've got that underlined twice, check the endpoints, okay? And I've added for measure here just the definition of extreme values. And this is the mathematical language stating that it's the lowest y value or the highest y value in its neighborhood, okay? All right. Local extreme values will occur when you have the derivative equal to 0 or undefined, okay? And a critical point occurs in the interior of the closed interval if you have the derivative equal to 0 or the derivative is undefined. The one other thing that this new version of the book has stated is that you have a stationary point when the derivative is equal to 0. Remember, I said if the velocity was equal to 0, your particle or body would not be in motion, it would be stationary. So they call those kind of critical points stationary points, as opposed to being when you have an undefined derivative, okay? I have an example of number 27 from 5-1 written out here so you can follow my logic, but I'm also going to do some examples here for you in your notes, all right? And you have some guided notes, hopefully with you today. So moving right along, and that's it. So let's go on to the guided notes. And I have my nice little document camera up and running, so you guys can see what I'm doing. And so what we're going to do is we're going to find the absolute extrema for this function analytically or using some algebra. Now, you and I are very wise people because we've taken pre-cal and we know what kind of function this is already. This function is a parabola that opens up. So we already know that this one's going to have some kind of absolute extrema if it was an open interval. We don't know where the vertex of this parabola is. So we would have to do completing the square, which I know you're not in the mood to do right now. But let's use some calculus and see if we can find the extreme values of this function over this closed interval. So the first thing you have to do is take the derivative. So here we go. We're going to take the derivative, and that's going to be 8x minus 4. And then we're going to set the derivative equal to 0 to find out where any horizontal tangents are. So that is going to give us 8x minus 4 equals 0. We get 8x equals 4, x equals 1/2. And now I'm going to do an xy chart or an xf of x chart to see or compare the values. So I'm going to put on this chart the endpoint. So here it goes an endpoint. And then my critical point is in the middle of this interval. So I have to put that on my chart. And I don't always write these down. I'm just showing you for illustration purposes. And then we're going to put a 2 here, and this is an endpoint. Now let's plug in these values in our function and see what's happening. What happens when I plug in x equals 0? You get 1, clearly. And then what happens when you plug in 1/2? Well, I have taken the liberty of doing this ahead of time to make this video less lengthy. And I found out that that value turns out to be 0. And then when you plug in 2, you're going to get 9. So if you were thinking about it, what's happening to this function between 1 and 0? Well, it's going down, right? The value, it's decreasing. So this is going to be the absolute minimum because it's the lowest y value on our list. And this function, this set x equals 2 is going to be our absolute maximum because it is the highest y value on our list. And now we have to decide what's going on with this part. Well, what's happening here? Now my function is decreasing from 1 to 0. So if I'm decreasing from 1 to 0, that means this had to be a relative maximum. So the good news, which you all love to have good news, I know, is that the AP people take this as enough justification for absolute extrema on a closed interval. So that's great news. So let's try another example that's a little bit more complicated. All right. Or actually, let's use technology. And I've got Desmos up here. And let's see if we can write here y equals 4x to the second minus 4x plus 1. And I'm going to delete all this because that was from an earlier class. And we can restrict our domain here using curly braces. I don't know if you remember that, but we can say from 0 less than or equal to x less than or equal to 2. And there it is. And you can see from the curve that we are correct. If I were to plot these points, we would say 0, 1, whoops, 0, comma 1. I wish I had my drivers here. I'm not as good at typing as you guys are. So this would be 0, commas, or no, I'm sorry, 1/2. Comma 0. Show the label. And then 2, 9. So 2, comma 9. And show the label. And there you go. And it turns out that the vertex is in this interval, which is pretty cool. All right, moving right along. Let's do another example. A little bit more complicated, but not impossible. First of all, is this a continuous function? The answer is yes, because the denominator will never be 0. If you set x squared plus 2 equal to 0, you get x squared plus 2 equals -2, which gives you no real solution. So this one is never 0 on the bottom, which is nice. And we have a closed interval. So by the extreme value theorem, we are guaranteed to have an absolute max and an absolute minimum. All right, so the first thing we do is we take the derivative of this function. So f prime of x using the quotient rule, which we all know and love, is going to be ho d high minus high d ho all over ho, which is x squared plus 2, quantity squared. And let's simplify things. F prime of x equals, this is going to be x squared plus 2 minus 2x squared all over x squared plus 2 quantity squared, which gives us 2 minus x squared on top, if you add those together to simplify. And then we get x squared plus 2 quantity squared as f prime of x. And now we're going to set it equal to 0. Well, the denominator, as we spoke about a moment ago, will never equal 0. So then we're going to set the numerator equal to 0, which will be 2 minus x squared equals 0, x squared equals 2, x equals plus or minus root 2. And root 2 is about 1.414. So this is not going, the negative one's not going to be in the interval. So so lucky for us, we are going to just do a chart. I'm going to do it over here so that we can keep it all on the same screen. F of x chart. So what do we put on this chart? Well, we're going to put our endpoints, which are -1 and 4. And then we're going to put any critical points that are in the middle of the interval here. And so x equals root 2 is going to go in here in the middle. And now we're going to find the y values for these x values. So when I plug in -1, I've already done the liberty of finding out that that's -1/3. And when I put in the square root of 2, I get the square root of 2 over 4. And then when I plug in 4, I get 2/9. All right, so when I comparing these y values, you all can agree, I'm sure, that this is going to be the absolute min. Now, there's some concern as to which one is the bigger number here. Well, 2/9, and this is going to be 1.4 over 4. And believe it or not, this is going to be the largest number. This is the absolute max. This is about 0.25. And then what's happening to this, if this is the absolute max, I have to decrease to get there. So this is going to be a relative minimum. All right. So let's go to Desmos and see if it works. All right, so we're going to take our function y equals x divided by x to the second plus 2, and then we're going to make our interval here -1 to 4, and we're going to put our points on here, which is going to be -1, -1 divided by 3. There we go. We're going to keep the label there, and then square root 2 divided by 4. No, I'm sorry, it's just square root of 2. And then it's square root 2 divided by 4. I'm going to get rid of the 0 here. And you see that that's the maximum there. And then the next point is going to be 4 divided by 9. And we're going to show the label. And there it is. So we see that we have the absolute min occurring at -1 as we predicted. And we have an absolute max at root 2 and then a relative min at x equals 4. All right. So what would happen here if, for some reason, and I'm extending here, which you absolutely love, I know. What happens if I don't restrict the domain on this function? Well, what do I mean by that? What if I said I wanted to find the extrema here for this function, x over x squared plus 2, but my domain was unlimited? Well, then how does this problem change? Well, it changes a little bit. First of all, endpoints can't really go here, can they? Because I don't have any endpoints. But we still need to consider what's going on at the infinities. All right, so we're going to still, excuse me, put our critical points on here. So that's going to be -√2 now because it'll be in the interval and root 2. And when I plug those in, we're going to get -√2 over 4 and root 2 over 4. And I suspect that this is going to be a minimum of some kind, and this will be a maximum of some kind. But in order to know what kind of, whether they're relative or absolute, I need to do the end behavior limits. So let's do the end behavior limits. The limit as x goes to infinity of x over x squared plus 2, you see the limits never really go away, which I know you're really thrilled about. So what happens when I do this, if I compare the degree of the numerator and the degree of the denominator, or put in 1,000,000 over 1,000,000 squared, we get 0. What about the limit as x goes to -infinity of x over x squared plus 2? Well, guess what? That's also going to 0. So what does that mean? That means that these places here are the only places where I'm going to have extrema, because these values are larger or smaller than where the function's headed. So that means that this is going to be the absolute min. And this one will be the absolute max. And if we go back to our Desmos graph, where I am restricting here, and I take that off, and you see now where if I make this bigger, that this root 2 is absolutely, the largest y value at 0.354. And this point here will be the, where's the absolute minimum? Right here, which is negative 1.414 and negative 0.354. So this is the absolute max now, and this is the absolute min, and the end behavior shows you that there can't be any other extrema for that function. All right, so another example really quickly. What happens if I have a power function and a line together? Well, first of all, this function is continuous because I don't have any denominators that'll be equal to 0, no jump discontinuities or removable discontinuities, and I have a closed interval. So I'm guaranteed to have, by the extreme value theorem, absolute max, absolute min. So we're on the hunt for that. So the first thing we have to do is take the derivative. But I don't want to use the product rule here. I want to make things easier on myself. And before I take the derivative, I'm going to multiply this out. And we're going to say that this is 20x to the 2/3 minus, and I'm going to add the exponents here because this is really an exponent of 1. So 2/3 plus 3/3 is equal to 5/3. And now I'm going to take the derivative, and we get 40/3 x to the negative 1/3 minus 5/3 x to the 2/3. All right, now I'm going to do something that makes you uncomfortable because I like to do that. I'm going to factor out a 5/3, which is not difficult. And I'm going to factor out the most negative exponent here, which is x to the negative 1/3. Let's write that better. When I do that, I'm left with 8 here minus 5, x times, now when you factor something out, I'm going to take this x to the 2/3 over here and divide by x to the negative 1/3. And when you're dividing, what you do is you subtract the exponent. So this would be 2/3 minus a minus 1/3, which gives you x to the 3/3, which is 1. So something wonderful just happened. And now I'm going to put things where they belong. And we're going to get 5 times 8 minus x over 3 times the cube root of x. So that's f prime of x. So now I've got to find out where this function is 0, or where the derivative is equal to 0. So f prime will equal 0 and the numerator is equal to 0. And that's going to be when 5 times 8 minus x equals 0, which occurs when x equals 8. And f prime of x is undefined when 3 cube root of x is equal to 0, and that's going to occur when x equals 0. All right, so we're going to have 0 on our chart because that's in the interval, and we're going to have 8 on our chart because that's also in the interval. So we're going to have 4 numbers on our xy chart here. So we're going to have x, f of x. So let's plug in the numbers. Negative 1, I'm going to put them in order, 0, 8, and then 20. Nice ray of sunshine here. And f of x, let's remind ourselves, is x to the 2/3 times 20 minus x. All right, so when I plug in negative 1, we're going to get 21 here, and that's going to be the cube root of negative 1 squared, which is 1, so this will be 21. When I plug in 0, I get 0. When you plug in 8, you're going to get 12 here. And then the cube root of 8 squared is 2 squared, which is 4. 4 times 12 is 48. Wow, that's a big number. And then when we plug 20 in, which is scary as 20 might have looked, when you plug 20 in, you get a 0, so that's nice. All right, so just looking at these numbers, you can tell that the zeros are the absolute minimums. After yesterday's rain, it's really nice to have the sun shining today, so sorry about the shadows there. Absolute minimums. Now, I said in the very beginning on my PowerPoint, you can have more than one absolute minimum if they're the same y value occurring at two different x's, so that's fine. And this number here, 48, obviously is the highest y value, so this will be our absolute maximum. Now, what do we do about this one? Well, we have a function that's 21 and going to 0. So 21 going to 0. So that means that has to be a relative maximum. Because it's decreasing afterwards. I should take the S off here. It's only one of them. There's two of them, but they're at different X locations. All right, so just remember there can be more than one place that an absolute max can occur. All right, so let's verify our answer here by going to Desmos. And so we're going to say y equals x to the 2 divided by 3 times, whoops, I don't want the times in the exponent, bring it down here, times 20 minus x, close parentheses. Oh, wow, well, oh, I've got y equals, that's why it's not happy with me. All right, well, I feel better about that now. All right, and we're going to put our points on here, -1, 21, and 0. Whoops. I should be a faster typer so this video go faster for you. Sorry about that, but you know. And then 8, 48, showing the label, and then the last point was 20, 0, and we want to show the label. All right, so I need to like zoom way out here. Wow, there it is. And so, wow, so we can tell right away that on the closed interval from negative, well, let's make our interval closed using the curly braces because we can with cool Desmos, -1, less than or equal to x, less than or equal to 20. So there we go. We can see that our analysis using the algebra worked out just fine. We have our relative maximum here on the left at x equals -1, our absolute maximum at 8, our two absolute minimums at 0 and in 20. So that's pretty cool. All right. Of course, trig, because you guys love trig so much. I don't know what to do with ourselves, right? We love trig so much. All right, so let's do a trig one to prove we can. I've got a closed interval from 0 to pi. First things first is to take the derivative. So this will be f prime of x equals, let's do that. What's the derivative of sine? Not all at once, or all at once, cosine x, minus the derivative of cosine, which is negative sine, which makes this plus sine x equals 0. Wow, this is a trig equation, and it's equal to 0. Now, rolling back the tape to pre-cal, what you do when you have a sine and a cosine and there's a 0 in it, in the equation with it, is you move the cosine over and you divide by cosine. Now, I told you a long time ago not to divide by a trig function. If it would go away, you'd lose a solution. But this cosine doesn't go away, it gets embedded into the sine over cosine, which is a tangent. So tangent of x is equal to -1. All right, well, what quadrants is the tangent negative? Well, that would be in quadrants 2 and 4. So alpha here is pi over 4. So my first critical point is going to be x equals 3 pi over 4, and the next critical point will be the fourth quadrant 7 pi over 4 angle, which is 7 pi over 4. So on my chart, I am going to plug in the endpoints, which happen to be 0 and pi. And I don't have to worry about the 7 pi over 4, do I? Because that one is outside of this interval, which is nice. So I'm only going to put one point on here, which is 3 pi over 4. And now let's plug in 0 into our function. Well, the sine of 0 is 0 minus the cosine of 0, which is 1. So this is -1. And when I plug 3 pi over 4 in, we're going to get root 2 over 2 minus a minus root 2 over 2, which is equal to 2 root 2's over 2, which is root 2. And then when I plug pi in, the sine of pi is 0, but the cosine is -1. So 0 minus a -1 gives us a +1. And just remember that root 2 is bigger than 1. It's about 1.414. So what wins? I am the absolute minimum. Well, this one right here, because it's the lowest y value. This is the absolute minimum. This is the absolute maximum. And this is a relative minimum. Now, why is it a relative minimum? Well, I'm starting at a maximum, and I have to go from the maximum downward. So this would be root 2 going down to 1 in the y values. So do you see how that would be a minimum? All right, so I know you guys are a little bit shaky or feel like you might be a little bit shaky on trig functions. So let's look at this graph because we can with Desmos. And let's make our graph sine x minus cosine x. And we're going to limit our function from 0 to pi. And I can zoom way in now because obviously a lot smaller. All right, so we're not going to have -0, but 0, and then our other point is going to be our y value is -1. Clearly the absolute minimum was we suggested. And then we're going to say 3 pi over 4. 3 pi divided by 4. Square root 2. There it is. That's our absolute maximum right there. It just appeared on screen. And the last point will be pi, comma 1. And that is our relative minimum. And we're going to get rid of this one. So you can see that our chart worked out perfectly, which is really cool. All right.